the virtual environment or the virtual machine, the code spaces, so to speak. And once that is here, actually, let me just keep it like so. Okay, you should see some environment like this. These files may not be visible to you. It was just because, for me, it is because I was working on this prior to recording this video. And now let's kind of head back to what our intention was, and let's discuss a few things about that. Okay, so what we wanted to do was boot the CPU. And then we said that the stack pointer and essentially whatever is at location hex offset hex 4, not location, but offset, that will be put in program counter, right? So this, the first value goes to SP, the zeroth offset value goes to SP, and the fourth offset value goes to program counter. And these offset are from the start of the code memory, right? So zeroth address here will be SP, and the fourth address would be put into program counter, right? So that is what we argued. That is what we want to prove, or at least get an evidence for. So now then, what are we going to do with our virtual code space environment, so to speak, the virtual machine environment? Okay, so we talked about the fact that well, first off, we'll write some code. So that code is in foo.s, and then we are going to have a make file. And this is purely for automation. Make files are just for automation instead of typing commands by hand. We will kind of, list them in a make file and then have the make utility execute those for us. And we'll discuss a little bit about this in some time. But this is where our assembly program will live, at least for now, right? And we are going to write like, few lines of assembly code here. And our intention is that wherever the program counter is pointing, those instructions be available there, right? That is what we want. Okay, and then the third thing we have is map.ld. Now this name doesn't matter here, much like the name here doesn't matter. This name matters. Okay, so the map.ld is essentially a linker script. And we'll come to what linker script is. And the linker script guides on how to position things in the memory, how to place stuff, let's say, and what stuff is, we'll come to that also, stuff in the memory. Right. So there are three parts there. We have an assembly file, we have a make file, and we have the map.ld file. So now the thing is, we take the foo.s and what we want to do is feed it to assembler. Assembler is a utility. We want to feed it into the assembler relating to ARM, the assembler that understands the assembly for ARM, and then we want to get an object file out of it. Right? So what this means is that the assembly is now converted into zeros and ones. Instructions, machine level instructions have been, or encoding has been generated. And then what we do is we say, hey, take this map.ld, which is the linker script file, take this object file, and then we feed it to the linker. And then the linker will generate an ELF, which is the final, so to speak, executable file. And in that file, the instructions and the contents, so to speak, are placed as dictated by the linker file. Right? And all of this becomes clear once we go back to our code spaces and I walk you through the files. But then what we want to do is generate this ELF and then feed this ELF to QEMU, right? And QEMU, what we are going to ask it to do is uh, operate like a Cortex-M3 CPU. So now what will happen is QEMU will consume this, so to speak, firmware. We can call this firmware. And then QMU will look at the instruction, decode them as if an M3 processor would do it, and then operate on those instructions as if the M3 processor will do it. Right? And what we are also going to do is we are going to ask QMU to open a socket for debug and then connect GDB to it. And then using GDB, we can look at what is going on within the CPU at a programmer's model level. And all of this again becomes super clear as we go back to our code spaces and do things. But then here's the thing, we have foo.s, just a recap, we have the make file. Right. This is strictly speaking not required, but it makes life easy for us. So we have it. And then we have the map.ld. Right. This is for assembler. This gives us foo.o. Okay, this is foo.o. This then, along with this, is fed to the linker. The linker will give us foo.elf, and then we take foo.elf and feed it to QEMU, and QEMU is acting like a Cortex M3 machine, an M-class CPU, but the microarchitecture is M3. And then this kind of exposes a socket to which we connect GDB, and using GDB we kind of look inside the M3 processor at a programmer's model view. And what is our intention with going the GDB way? So the GDB, because it shows us the internals or gives us a way to look at internals of the processor, we'll be able to look at the stack pointer and program counter register to conclude whether or not the values are exactly loaded as we expect them based on the idea of vector table. So vector table, recall, the first entry within that was supposed to be stack pointer. The second was, well, it was called reset handler, and we said that this goes to program counter, this goes to speed, then there is something here. So we want to verify whether or not the M-class CPU behaves in this way, where it copies over stack pointer and program counter. So this kind of is the flow of things. This is purely for automation. Right? And I'll kind of demonstrate that now. So let's go back to our code here, or our working environment here, and few things that I want you to notice, which is there is foo.s here, right? It is available here. Then there is make file available here, map.ld, and then essentially these are the three files that we talked about. Okay, perfect. So before we dive into the assembly, what I want to show is the make file, just so that few things are clear. And let me kind of go ahead and increase the font size. Okay, so these are again, we have like a separate course on Makefile, and if you've got like the firmware engineer's arsenal bundle, then that would be covered. The make course would be covered in that. So do take a look at that. Spend time learning Make. Very useful to know as a firmware engineer. But here I'll just go over what is happening. So first off, let's come to these three lines later. Let me also change the color. Yeah, this one's good. Okay, we'll come to this in a bit. These three, or these two lines here, if you notice, so we are taking the ARM assembler. AS is for assembler, and everything before that is like a naming convention, so to speak, for the utility. But AS is the assembler. We say, hey, assembler, take the foo.s file and please generate the foo.o file, right? So this is where we are going from foo.s to foo.o. So at this line. On the next line, the LD here is the linker, and to the linker we are saying, hey, take the map file, map.ld file, so that you understand how to place things, and then take this object file foo.o, and then kind of convert that into foo.elf. Now elf is the actual, so to speak, executable file that QEMU can consume. Now, at this point, the last line here is where we are calling or invoking QEMU. We're saying, hey, behave as if you are this board, and we'll come to what board is. And by the way, it has this CPU, and we don't want you to raise any graphics or any window for any graphical related things. We just want you to straight up go execute the ELF. And oh, by the way, we also plan on connecting GDB. So expose a port for GDB to connect to you, and that port is 1234 on TCP. Okay, so now let's talk about what this is, and what this is. So these are essentially variables in Makefile, and at this point, variables are being dereferenced, and those variables are defined here. So CPU we are saying is Cortex-M3, and the board is STM32 VL Discovery. Now, what is a board? So it turns out that QEMU doesn't just implement a processor; it implements the machines and boards. So if we were to type QEMU in the terminal here, um, uh, okay, let's see QEMU system right, and if I do minus machine help, we'll see that it has printed list of machines that it implements. Right, there are so many of those. And the one I chose was STM related, or it had the name STM 32VL Discovery. And if you see, it actually implements a development board as a software, which is super cool because then what we do here can also be done on a physical board. So, and that implements the Cortex M3. So this is one reason why I have also specified board here, because I want QEMU to behave as if it is it is kind of the STM board on which there is an M3 processor. Okay, so now let's go ahead and look at what this board is. So it happens to be a board of this nature. It is made by ST Microelectronics, and I've also ordered this board. So towards the end, we'll also run our experiments on a physical board. So whatever you're learning right now using QEMU, rest assured that it also applies to real world scenarios. It will work on a real board as well. And we'll come to this towards the end of the course, but then this is what it is. And this board then has this controller chip on it, the STM32F100RB blah blah blah, and then we can actually go ahead and look for the data sheet documentation, and then let's go. Let's see if I can find the data sheet somewhere here. Mm, the data sheet will give us information about how this controller is. Yeah, maybe we'll come to that in a bit. Let me see if I can just find out. Nice. Let's go here. Yes, let's click here. Nice. So this is then, giving information about this controller. It has this much of memory, this much of SRAM, so on and so forth. What we're interested in right now is something called the memory map. So this memory map, if you recall, is essentially a layout of at what address we have what. And so the interesting thing here is at the 0th address, it says this 0th address is alias to flash or system memory depending on boot pins. So essentially it is going to be mapped to flash memory and we can, like, depending on boot pins, it can choose one memory versus another to boot. We can safely assume that it will boot out of flash, and then flash kind of, wherever it is, we just say that, 0 address is from where it will start to execute things. That's how it is. Okay, so then what was the point of us coming here? Well, just wanted to reiterate to you that the board I have selected has an M3 processor on it, and it's also a real board. Okay, perfect. Now let's come back and talk about these two lines. So these two lines are essentially the object dump and read ELF utilities, which are kind of going or consuming the ELF and extracting some debug related information for us. That's what they are doing. And the debug, ELF debug here, we'll kind of look at this file. It gives us some information as to, where is what section, which instruction set, so on and so forth. All right. So this last line here is then what launches QEMU, and the GDB multi-arch, whatever here. This is our way of launching a GDB and connecting it on port 1234 where QEMU is available. And then last thing here is essentially us having a command to remove temporary files, right? Okay. So now the something something colon in a make file are essentially called targets, and these are called the recipes, right? So when I execute make QEMU, these commands get executed. When I do GDB make GDB, this command gets executed, and when I do make clean, this command gets executed. Yeah. Now then let me go ahead and full screen all of this so that we have real estate to ourselves. Then also let me get myself, actually let's put this here, and then yes, just so that I'm out of the way and we can see what files we're dealing with. Perfect. Okay, so let me then just go ahead and do make QEMU. What you should see happen is this file gets generated, this gets generated, this file gets generated, and this file gets generated. And also you'll see all these 5 commands getting printed on the screen. So if you see, the 5 commands got printed here, so it executed them one after the other. That's the idea. And if you also see, the files are generated here. We'll take a look at these files in a bit, but I first want to show you, straight up the connection between QEMU and GDB. So I kind of created a split terminal here, then I'm wanting to drag it up here. So now I have 2 terminals, one at the bottom, one at the top. In the top one, I simply say make GDB. So what happened here was, right, what happened here was GDB essentially connected on the port. Then it figured that, okay, foo.elf is what we were executing. And then it went ahead, connected, and the processor was halted at this instruction, this instruction right here. We'll come to the foo.s file in a while, but look at this. So the registers, the CPU registers, the programmer's model that we talked about is right in front of us, right? So R0 through R12 are the general purpose registers. Then R13 is represented as SP directly here, stack pointer. LR is the link register, and PC is the program counter. And XPSR was the program status register. So all the registers are available to us. And this is how now we can execute assembly and use GDB to kind of look at what the processor is doing, right? So if I were to, at this point, for example, do NI, you'll notice that the R1 value changed, so did the XPSR, and so did the program counter, right? And again, we'll revisit this in a bit because I haven't explained other files. So use the Q command here on the prompt on the GDB to quit GDB. So put a Y and you're back to the terminal. And then here to exit QEMU, press Control A, then release the button followed by an X. So Control A, release the buttons, then just the X key that will kind of exit QEME, right? Okay, so we kind of ran through one experimentation here. Now let's go to foo.s. There is like a little bit of noise here. There's a lot of things going on. So first off, these four are the assembly instructions. Right? So these are assembly instructions, and this part here is essentially full of something called directives, and all of this becomes clear in the later lectures, why structure it this way and so on and so forth. And same with this. So this is also kind of relating to directives. And actually, made a mistake here. Everything's a directive. These are also directives. So what we are doing is we are saying, hey, assembler, I am declaring a section here, and that section's name is vectors. So when you're searching for sections to be picked, know that everything follows is by the name dot vectors. And then we say, okay, let's put a label here called vector table, and this is a label, some name followed by a colon. That's a label. A label is a friendly name to kind of point to a location. That's what it is. Then we say, okay, when you're starting wherever this vector table location is or label is pointing to, I want you to put a word there. Word is 4 bytes worth of information. And the word is just hex ABC0. Right? You can change this to become any other hex number. This is just a random hex value that I wanted to put because my intention was that this will go in the stack pointer, right? Y also becomes clear in a bit. Then I'm saying the next word that I want you to put is called the reset handler. And again, what is special about reset handler? Nothing. It's just a name. It's a name that's representing a memory location. Then we say, okay, once you have put these two words here, fill the rest of the space with zeros. And how many zeros? Yeah, okay, 400 of those. So, and this is just so that, so we have the stack pointer, program counter, or reset handler, and then there were other exception vectors to be filled, which we are not filling. So I'm just skipping 400, bytes, and it's just like skipping 400 words just for safety, right? And also because of the fact that I'm not filling in the rest of the vectors. So then after that, we say, hey, now a new section starts, and that section is called text. And text is where the code lives typically. Wherever the code is, that is called the text section. And then we are saying, okay, and oh, by the way, if you're not on an aligned address, so make sure that the address is aligned to the power of 2. And what power of 2? The first power of 2. So aligned by essentially 2 at a 2-byte boundary. And why is this important? It's because the ARM controllers fetch instructions from a 2-byte boundary, 2 or 4-byte boundary. The instructions can be 16-bit or 32-bit. In our case, when we compile them with the mthumb option, they compile to 2 bytes. Again, if all of this is confusing, just kind of focus yourself on the higher level objective here, because the details you'll end up learning as we progress through the course. So we are then saying, okay, align the address at a 2-byte boundary, and by the way, this reset handler is of the type function. So whenever you're trying to jump to this, make sure that you treat it like a C function. And this is more, well, the C function part, I think, jumped the gun, but this is more of instructions for the assembler, the AS utility, as to how to treat the code and the various parts of the program, right? So we'll come to this maybe later. It will make more sense later. But then this is a label here pointing to the memory where there are these 4 instructions. So when assembler consumes them, or this file essentially, it will read through, figure out what needs to be done, and then it would be like, okay, I know that there is a vector table label which has certain information. There is reset handler label that has certain information. And now I need instructions on where to put those, how to go about, populating the memory, so to speak. And that's where the map.ld file comes in. So what we are doing at a high level here, we are saying, hey, we have a memory that starts from 0 and has some random length. In this case, I think this is 16 KB. Uh, Anything around 4 KB is fine. I chose it to be, 16 KB. This ideally should be the size of the memory that the board supports. I just chose it to be 16 KB. I know that the board supports more than 16 KB. So this is fine. You can play with this number also. Then what we are saying is, okay, now we are going to guide on where to put the sections in the ELF. And sections are essentially chunks of a binary file. Right? And typical chunks are like the data section, the PSS section, the text section, so on and so forth. Again, this is in detail covered in the linker scripts course if you prefer to learn all of this. So at a high level, what's happening here is we're saying, hey, create a text section in the memory which starts from here, and go ahead and put the vector section first, right? Vectors followed by whatever. This is a wildcard. So it will take and put vector table, or sorry, it will take and put the vector table content here because vector table was part of the vector section, right? So it will take, okay, let me take the vector section and it will take all of this, right, this information and put it first in the memory, right? So the first thing that gets put is the vectors. And so as a result of this, we'll have the stack pointer and the reset handler as the first two words, followed by 400, a whole of 400 bytes, and then followed by the text section, which happens to be, if we go back here, which happens to be the reset handler. Right? So effectively, what is happening here is we are having two words with stack pointer and reset handler, then 400, a space worth of 400 bytes, skip essentially, and then we have the code starting here. And we don't know what this address is. So we'll now kind of go ahead and figure that out. So hopefully you're convinced about what the assembler and linker is doing. And I need to kind of adjust my sitting posture. Okay. So what we are going to do now is run QEMU again and then investigate as to what the stack, like, did the stack pointer get loaded? Did the program counter get loaded? And where is the program counter pointing to? So let me go ahead and do make clean. And when I do make clean, you'll notice that all these files are deleted. The files that were automatically generated are gone. Now I do make QEMU. Okay, all the files are generated. QEMU is started. So I'll go to bash here and do make debug. Oh, sorry, make GDB. All right, perfect. So what we notice here is program counter is having this value of 196, hex 196, and the stack pointer is having the value of hex ABC0. Now this, I think we can conclude that had to be ABC0, and it is exactly that. And why did it have to be hex ABC0? Because we deliberately put that number here, right, as a random number, just so that we can identify. And the program counter, the hex 196, my claim is it was pointing to the reset vector. Well, it was at least okay. At least GDB was, here. If you see 11 is highlighted in green, that means the program counter is pointing to this location, wherever this assembly instruction is, and that happens to have the label reset handler. So now the question is, how do we know at what point our code was starting, right? Where was the reset handler starting? The hex, oh, sorry, this is hex 98, not, I'm blind. So this is hex 98, not hex 96, right? Okay. So what we want to do now is go to the LST file. And if you see, the LST file is essentially the assembly instruction with a lot of debug information. And so what we'll notice here is there is reset handler here, and then it kind of points to 198. So before the colon here is the address, and after the colon is a number that represents this assembly instruction, right? So 198 is essentially the location where this instruction moves R1 comma where hex 1 is present, right? This. Okay. And what is the debug file? Well, the debug file is talking about, okay, the machine is of the ARM type. It will also talk about, I think, okay, let's see. Yeah, it has information about different sections. The text section starts from 0. It has a size of these many, so on and so forth. So, where are stuff loaded, stuff like that. And so debug file essentially helps us with some background information. We won't be using it as much, so we don't care about it. But the LST file, yes, if we see the vector table starts off at the 0th address, the first and the first offset, we have this, and the fourth location from this, we have this, and then the reset handler is at 198. So that's exactly what we see. Now, just for the sake of completion, just to kind of appreciate that the CPU is actually doing something. If I type the gdb command ni, that means execute the next instruction. So it will go ahead and execute this, which means it will move. And again, what the assembly instructions mean, we'll come to that. But right now, just trust me. And when we say move R1, comma 1, it means take 1 and load it into the R1 register. So when I do ni, we'll notice that R1 is loaded with the value of 1. The program counter has moved ahead by 2 units. So it was 198, now it has become 199 and 198. A in hex is 10. So, from 8 to 10, it's 2 bytes worth of move. Now I'm going to execute again ni, and then now we see register R2 was loaded with the value of 2, and then the third one is essentially just adding R1 and R2 and putting the value in R3. So I do ni here, and we see that this sum or the addition is loaded, and also the program counter has moved by 2 bytes. All right, so what is this BL instruction? Well, BL is branch and link, and what it will do is, okay, let me go ahead and execute that. So what it did was, it kind of branched. This dot here represents the current location. So it branched to the same location, and it remembered that it had to kind of return back to this value. Now, when I do ni again, it simply kind of spins there. So it's a way of implementing a forever loop in assembly. Branch to the same location, so it goes on spinning at the same location. And that's that. So hopefully you're convinced about how the CPU boots. All the claims that we made earlier about the boot process, hopefully those are clear. And hopefully you have some idea about the linker file, why the make file was used, the LST file, and also the assembly file. And again, how we loaded the firmware into QEMU, got it to run, so on and so forth. Do play around with this, and starting next lecture, we'll dive into programming or understanding the assembly language. So I'll go ahead and then press Control A, Control X, and QEMU is gone. GTP, I'll just type Q, followed by S, and GTP is gone. So with this, I'll kind of see you in the next one.